In this video, I further investigate the Markov decision process. A Markov decision process is a tuple, includes a current state, action taken at the current state, state transition probability, future discount factor, incident reward, and the next state. So we define a state value function, action state value function, and a policy together to describe this tuple to formulate a complete one-step Markov decision. The policy is a mapping, the mapping from this current state to action A. And this state value function is an expected value. And this the Q value is also an expected value. This state value describes the property about the state S, and this Q function describes the property when an agent at state S after taking action A at this point. This R is incident reward. That means when an agent moves from his current state to next state, receive reward from his environment. This state transition probability also is called a system model or system dynamic. It's related to the environment, but it's a function of state S and action A. Here, this state value function is an expected value. That means we calculate the state value function at the state S1. We need to calculate the cumulative reward along episode from current state to the terminal state. And then we calculate all the value, the state value function along all the episodes and calculate the expectation of this sum along episodes. Here is this Q function is also an expected value. It's describe the property of agent at the state S after taking action A at this point. So to calculate this Q, we need to know this incident reward R from the environment. And also based on this state transition probability, we need to calculate the expectation of the state value function over all the possible next states, as is here. What we are interested in the reasons for the more reinforcement learning is to find the optimal policy. To find the optimal policy, we need to find the optimal state value function and optimal Q value function. This optimal state value function means we need to calculate what's the maximum value function at this state S. Because when agent at the state S under the policy pi, he can calculate the state value function for this action, for this action, for this action, and see which action will produce the maximum state value function. That state value function is the optimal state value function. Similarly, for the Q function, the Q function from this point, at the state S after taking action A at this point, and we have first we have this is the reward, and then under the policy pi, we have so many possible paths to calculate the return for this Q value function. And we are just selecting which policy, this action, and this policy pi, which action will make this Q maximum. That maximum Q value is defined as the optimal Q function. Once we have a Q, the optimal Q function, and then now we can find the optimal policy. That's our final purpose. For example, here, this is a current address state S. It has this state value function V. And this policy pi agent has so many choice for the action A1, A2, and so on. We have AK. And here, we need to know which action will generate a maximum Q value. The action generates the maximum Q value is defined as the optimal policy here. We know at least we have one policy at all the state in this domain. Make this state value function maximum at each state. That means as in this system, at least we have one optimal policy to make the state value function maximum at all the states. And then now let's see how can we use the Bellman equation to calculate the state value function and the Q value function. Use a Bellman equation to estimate the state value function under the policy pi. Of course, this is the expected value. First, the agent at this state, to calculate his expected value, we need to calculate the state value function over all the possible next state. All the possible next state together under this policy. We calculate the summation, and then plus this incident reward, we update the state value function at the current state. Similarly, for the Q function is here. We describe an agent at the current state after taking action A. At this state, we use this Q to describe the property of the agent at this point. Because the Q also is expected value, so we need to calculate this Q. We need the state value function over all the possible next state after this point, plus the incident value to update the Q value. Because this equation is a Bellman equation about the state value function, and this Bellman equation about the Q value function. Once we have this Q value function, and then now we can use the formula we introduced the last page. We can select the action A that makes this Q function maximum. That's the optimal policy we need to find. That's the whole story about the reinforcement learning. For more details, please check with this reference. Thank you. Bye.